Hello everyone. In this video we are going to discuss about tensile testing to know the yield stress, ultimate stress, breaking stress, percentage of reduction in area, percentage of elongation over a cage length, and modulus of elasticity of the given specimen. So in this experiment we are going to use any one of the following specimen. The first one is this is aluminium material, and these two are mild steel with varying diameters, and we are going to use this mild steel rod for our experiment. The following instruments are used for this experiment. First one is extensometer. So the extensometer is having the two dials, and its least count is 0.01 millimeter. So the maximum we can measure 3 mm length we can measure by using this extensometer. So there are different bars available for different length of extensometer holding. So the following instrument is used for measuring the extension of the specimen, in which these rods are used for measuring the setting range is 30 millimeter to 120 millimeter, and the another instrument which is used for measuring the diameter of the specimen is vernier caliper, and for measuring length of the specimen we are using the steel rule. So we are going to use this specimen having the diameter of 10.02, which is measured by using the vernier caliper. So when doing the experiment you may have these variations or deformation in the specimen. So according to Hooke's law, the stress is directly proportional to strain within the elastic limit or up to the limit of proportionality. So when it is reaching the limit of proportionality, you can see the first one, even though the load is applied, it is elongated, but there is no neck formation visible. And in the second load is also there, it is up to the yield strength. So up to this yield strength there is no material elongation is visible. Only the material elongation is visible, but the neck formation is not visible in the second diagram. The third diagram you can see the neck formation. So the neck formation is clearly visible at the time of ultimate load. Okay, the ultimate load is the maximum load. So once it is reaching the breaking point, you can see the breaking of the material. So before going to start the experiment, we have to do some pre-calculation to know the ultimate load and what kind of load range we have to select, and how long we can use the extensometer in the specimen. So according to this formula that you are looking at, we have to find out the ultimate load of the specimen. So here the ultimate stress assumed is 700 Newton per millimeter square. So the ultimate load can be calculated by using this formula, that is area into assumed ultimate stress. So area can be calculated from the diameter of the specimen. So in the side you can see the specimen we selected is having 10.02 millimeter diameter. So its area will be pi by 4 d square. So from that formula we are getting 78.81 millimeter square, and from this substitution we are getting the ultimate load value as 55.17 kilonewton. So for this we have to select the load ranges. So in our machine we are having 4 load ranges. One is up to 0 to 40 kilonewton, and 0 to 100 kilonewton, and 0 to 200 kilonewton, then 0 to 400 kilonewton. According to our calculated value of ultimate load, the load range is being selected 0 to 100 kilonewton in our machine. So next, how long we can use this extensometer? Because the extensometer, the setting cage is having different length. Okay, so we have to use this extensometer up to 0.7 times of yield load. Initially we are assuming the yield stress at 300 Newton per millimeter square for MS bars and 400 Newton per millimeter square for tar steel. So our selected material is MS bar. So we have to select 300 Newton per millimeter square. Next, the yield load can be calculated from this yield stress into area of cross section. So the yield load here, the use of extensometer is equal to 0.7 into 300 into cross sectional area, because here the assumed yield stress is 300 and the cross sectional area already we have calculated as 78.81. So from this calculation we are getting the yield load as 16.55 kilonewton, up to which we can use this extensometer. And the gauge length for determining percentage of elongation is having this formula 5.05 into root of A. A is cross sectional area, that is already calculated. By substitution we are getting 44.83 millimeter. So we can select the setting gauge length as 50 millimeter. So in this extensometer, as I told, there are different bars, setting gauge bars available. So in which we have to select the 0 to 50 range.
So as of now, you guys would have seen about how to make use of the extensometer. Before getting into the experiment, what are all the preliminary steps that we wanted to come across. So all those sort of steps you have seen. Now with respect to the machine, so this is a universal testing machine which has got a maximum capacity of 400 kilonewton, out of which there are different ranges in which the load can be operable. So which shows the total range of the machine as varying from 40 kilonewton to 400 newton. So the corresponding valve or the needle shows what are all the variations we can make use of, like 40 kilonewton, 100 kilonewton, 200 and 400. So these are the four ranges in which the machine can be operable. So based on the specific material, whatever we are going to test, accordingly the range of load can be suited. And now as of now, here we have set it up for about 100 kilonewton load. So maximum as of now we will be able to check a load of 100 kilonewton, where the total range is shown here, which varying from 0 to 100 kilonewton. Dial has got two needle. One is of blue color and the other one is red color. So blue color needle shows the actual reading at which the load is getting changed with respect to the material when it is under loading condition. And red color shows the follower needle. Once it reaches the maximum limit, red color would stop at that particular point to make us note for the ultimate value of the load. So this has got a range of, say as of now we have set up the maximum load as 100 kilonewton. So for 100 kilonewton it ranges from the changes that is occurring on the load would be with respect to 10 kilonewton. So 10, 20, 30, etc. So the corresponding least count of the division is given. So 0.2 kilonewton per division. So each division is of 0.2 kilonewton. Okay. So now with respect to the operating valve, so here we have two different valves for performing the experiment. One is of release valve. So the one is lying at the left is release valve, and to the right of it is of the operating valve. So initially, before the experiment is going to be started, after fixing the specimen into the crosshead, the initial condition of the valve should be in the closed condition. And before switching on to the hydraulic pump, here there is a two switches that is given in order to move the crosshead in the downward direction and upward direction, so that the crosshead will be subjected to move. So you can see the difference there. So now I am moving it in the downward direction. Same way the crosshead can be moved in the upward direction. Based on the length of the specimen, the height of the crosshead can be adjusted. So once the specimen is fixed on the two ends of the cross head, then later we have to close this valve, and further we have to switch on the hydraulic pump. So for switching on the hydraulic pump, there are two switches given. One is for on and for off. So this is the specimen. We are going to test the tensile strength of this particular mild steel specimen. The material is of mild steel. So the cross section of the specimen is taken as a dumbbell shape. The other way is you can call this as a dog bone shape. So where the gripping area, so this particular area refers to the gripping area of the specimen, and the intermediate position where we can be able to see it in a normal eye, so that would we used to call it as a gauge length. Okay. So now in order to mark the actual center of the specimen, so first of all initially measure the length of the specimen. It is of 200 mm. In order to mark the center point, so just locate the center of the specimen as at 100 mm exactly. So this is to make a note on the gauge length of the specimen in order to fix our extensometer. The extensometer will be operatable only under a gauge length. In order to locate the exact gauge length of the specimen, in which the extensometer is connected at the two ends of the pegs, so we are marking the central point of the specimen. In order to fix the specimen at both the ends, so the crosshead has got two jaws, so which is in the form of a V. So since we have a circular cross section of our specimen is of circular cross section, so the corresponding jaw is of V jaw. Okay. And according to the specimen cross section, the corresponding jaw has to be replaced. If you want to make use of a rectangular specimen, accordingly the corresponding jaws has to be modified. Okay. So here we have got the jaws which can be able to expand or contract based on the thickness of the specimen or the diameter of the specimen. So in order to fix it at the top, you just place the specimen with respect to the fixation and just tighten it. So this is just for the sake of fixing the specimen at the one of its end, that is normally at the topmost end. Okay. So now adjust the cross head with respect to the length of the specimen. Just move the cross head in order to fix it on the other end of the specimen. Make sure that the visibility of the specimen is clear. So whatever the alignment you wanted to make, so just rotate the handle and check if whether the corresponding specimen is under proper length or not. If required, further move the cross head . So right. So now tighten this clamp, and there is another handle to lock that particular position. Just rotate it and lock in that position so that the corresponding specimen won't get slipped out. Okay. So this is the way we will be able to fix the specimen onto the machine. So now the specimen is fixed onto the machine. So now we have to start the process by applying the load. So we have to give the constant load, that is a gradual load has to be given. So in order to apply the gradual load, we have this hydraulic pump where the pressure being applied in a gradual manner. So before the start of the experiment, just ensure two things. One is with respect to the load at which the range has to be checked. So this is the first point. So at what range of load our experiment has to be started. And next thing is, there are two different modes at which the machine can be operable. One is of analog mode and the other one is digital mode. So if you wanted to make use of a digital mode, obviously the system, that is the machine or the load has to be connected to the computer, and with the help of a software we will be able to calculate what is the maximum load at which the specimen get failed, that is ultimate stress value, and the corresponding deformation for each and every constant load or the gradual load. Now as of now we will not be going to conduct this experiment in a digital mode, so ensure that whether the machine is fixed in the analog mode. So next is to fix the extensometer. So as it was already instructed, like there is a certain maximum limit at which the extensometer should be operable. So in order to ensure that, you have to make use of a certain pre-calculation in order to find what is the maximum limit at which the extensometer is maximum limit at which it can be operable. Okay, so accordingly you have chosen the total gauge length of the pegs. Now already we have marked the center point on the specimen. So now with respect to the center point, just fix the extensometer. Where these two dials are clearly visible. And just lock the lock nut at that particular position so that it cannot slide from that position. So there is a lock nut to rigidly fix the extensometer at that particular position. So here is the observation table in which we are going to calculate the Young's modulus of the particular specimen. So there are different ranges of the load at which the particular specimen test has to be taken into consideration, and this range of load, whatever is specified here as 4, 8, 12 and 16 kilonewton, these range of load are within the elastic limit of the material. So within that limit only we will be able to operate our extensometer based on the pre-calculations. Okay. So for the corresponding load of 4 kilonewton, what is the corresponding deformation that can be seen from the extensometer or from the left dial and the right dial? An average of these two values can be taken and consider that as a corresponding deformation value for the particular load of 4 kilonewton. And we know the respective load and the corresponding area of the specimen, and load by area will give you the stress value for the respective load of 4 kilonewton. And similarly, we have calculated the deformation from the extensometer, and as we know, like strain is nothing but the total length of deformation divided by that is change in length divided by the original length. Now from the deformation value, whatever is arrived out of this average, that gives you the change in the length divided by the original length will give you strain. And so the Young's modulus of the specimen can be calculated from the graph after plotting the graph with respect to the stress value and as well as the strain value, so that we will be getting the exact elastic limit in as a linear line, and from that linear curve we will be able to calculate the Young's modulus. As we have mentioned earlier, extensometer is operable only from the elastic limit. So stress varies linearly from 0 to the particular point, so at which the elastic to plastic transition occurs. So normally elastic to plastic transition occurs at that point, we used to call it as a yield point. So from the origin to the yield point, the entire limit we used to call it as an elastic limit, where it obeys the Hooke's law. So within the elastic limit, stress is directly proportional to strain. Okay. So from this range only, from 4 kilonewton to 16 kilonewton, we are considering to be an elastic limit, where if you are after plotting the graph, you will get the linear line, and from that linear region, we will be able to calculate what is the Young's modulus. That is, slope of that particular linear line will give you the Young's modulus of the material, which is stress over strain. So we are going to switch on the machine. So we have ensured like two valves are under closed condition, and now switch on the hydraulic pump in order to give the gradual load. So after switching on the hydraulic pump, now release the valve slowly, gradually. So you can monitor the same. You can open the valve in the counterclockwise direction, and you can monitor the amount of load that can be applied from the dial. So the needle will start to deflect, and we can ensure that the respective load is applied on the specimen. Now the needle is started to deflect. Now just fix the valve in that particular position so that gradual load is applied onto the specimen. Now at 4 kilonewton, we have to measure what is the respective deformation. We can see the readings from both the dial, from the left dial and the right dial. It reads 0. So for 4 kilonewton, there is no deformation. So the respective dial reads 0, left dial and right dial. So just make a note of that value and just now the load is gradually started to increase. Once it reaches 8 kilonewton, now the load has reached 8 kilonewton. It reads 0.01, right dial reads 0. Same way, when the load reaches 12 kilonewton, check the deformation in the extensometer. Reads 0.03 and right dial reads 0.01. Once the needle reaches 16 kilonewton, just make a note on the deformation value. Note down the value of the deformation for 16 kilonewton from the extensometer, as the left dial reads 0.05 and the right dial reads 0.02. So now the corresponding experiment progresses as such. So once it reaches the yield point, so the yield point refers to the point at which the elastic to plastic transition occurs. There is a point at which there will be a small deflection in the load. At that point, you can make a note of it as a yield point. So, further the experiment carries on, and once it reaches the maximum limit, so as per the stress strain curve, the red needle will stop at that particular point, and as per the stress strain curve, there will be a decremental in the value of the load, because the area of the cross section of the specimen starts reducing and the amount of load required would be lesser when compared to the higher amount at the ultimate point. In order to note the ultimate point, the red needle will stop at a particular location. Once the red needle stop at a certain point, that refers to the ultimate point of the particular specimen. There is no further progress on the load. Probably the ultimate load would reach at this particular point. So that can be ensured only if the blue needle started to retract back. Now the blue needle started to retract back, so that the red needle refers to the ultimate load. Now we have to make sure that at what load the fracture occurs. Now you will be able to see the neck formation of neck, that is the maximum reduction in the area. So failure will occur at a certain point. We will be able to make a note of that break. Braking load occurs at 42 kilonewton, and the maximum ultimate load of this specimen is 53 kilonewton. Now switch off the hydraulic pump and just close this valve and open the release valve so as to remove the specimen out of it. This is what the fractured specimen. There you can see the formation of a neck, that is the maximum reduction in the area, so which shows up a neck-like structure there. So where the reduction in the area has occurred. So normally the necking will occur at the ultimate load. Now in order to calculate the breaking strength or breaking stress of a material, we are in need of the neck diameter. So in order to measure the neck diameter, just fix the fractured specimen and make a note of the neck region. That is, neck diameter can be measured with the help of the vernier. The neck diameter is 7.24, and similarly we have to check through what is the final length of the specimen. Just place the scale and measure the final length of the specimen as now measure the final gauge length. After the deformation occurring, the final gauge length of the specimen is 160 mm. The final neck diameter has arrived as 7.24 mm, and we know that area is pi by 4 d square. We will be able to calculate the neck area as pi by 4 7.24 square, which is the final neck diameter, so that the neck area can be calculated. So we have come across different formulas to arrive out of different parameters. One is yield stress. We have make a note on the yield point load. So yield point load divided by the original cross sectional area will give you the yield strength of the material. And next comes the ultimate stress or ultimate strength of the material. So this is the parameter that refers to the actual strength of the material, at which the maximum resistance that body can offer or a material can offer. So which will be equal to ultimate load divided by the original cross sectional area. And next comes the breaking stress. Breaking stress will be with respect to the neck area. So that is the area at which the breaking occurs. So breaking load divided by the neck area will give you breaking strength or breaking stress of a material. And there is two different parameter. One is the actual breaking stress and the other one is the nominal breaking stress. Actual refers to the point at which the failure occurs. So that is what actual. So that refers to the neck area. And nominal breaking stress refers to the original cross sectional area of the specimen. So breaking load divided by the original cross sectional area. And next comes the percentage elongation. So percentage elongation, how much is the total elongation percentage, that is change in length divided by the original length into 100 that would give you the elongation in terms of percentage. In same way, how much is the total reduction in the area? So that refers to percentage reduction in the cross-sectional area is change in area divided by the original area. Here the change in area refers to the original area minus the neck area. Change in area refers to original area minus the neck area. Change in length refers to the final gauge length minus the original length. So now you might be familiar with the tensile test specimen, tensile test, how we have to calculate the ultimate strength of the material when it is under a tensile load. Thank you for listening.